All right, friends. So Canvas works again. This is great for us. We are finally in the last week of classes before I start the lecture. And by the way, these lectures this week will just be final review, nothing new. I do want to remind you of my late policy. So if there's an assignment that you missed in the class or there's an assignment that you got less than 50% on, if you do it again, you turn it in, or like 100% or whatever, I will give you half credit, remember. So that deadline is coming up. That's going to be this Friday. So the last week of classes, the Friday. So this Friday, 11:59 p.m. If you want to turn something in late, I will give you half credit. Okay? But that's going to be the deadline. And then remember when the final is going to happen. Of course, we're going to come into the classroom. It's going to be the Wednesday, right? Wednesday of finals week. Don't forget about that. The 20th. And yeah, I'll just be here to take it. You'll take it on the big computers, and then you will walk away forever. So there's nothing to do next Monday. You won't be coming to this room next Monday. You might have another final at this time, actually, depending on your schedule. So yeah, I think that's what I wanted to say about logistical things. I think I'm ready for the review if you are. Yeah, let's do it. So I just want to go over some like stuff for midterm one to start, just to remind us of things, because like you're gonna want to know how to make graphs and explore data and stuff like that. So my first silly example is a bit of an in-depth one, but here's my dilemma. I would like to review midterm one topics like tables and graphing and eventually hypothesis testing, just like exploring data. Here's the question we're going to ask. I love Trader Joe's very much, and I also love when things are cheap other than food. So if I want to retire one day, it's going to be a long time from now, but if I want to retire one day, here's what I want, all right? I want to live near Trader Joe's, and I want to spend as little money on as possible on housing and like cost of living. All right. So those are my two main requirements. Let's see where I should live. I've got some data on cities and their incomes, like the median income for each city that you could have in the U.S. I got that from the government. They've got some data on that, and then I've got I compiled my own data set of every Trader Joe's location. So without further ado, let's go there. I'll call this final review. So, first question, where should I retire? It's going to be a while, but you never know. They might make more Trader Joe's in the meantime. So let's make a table with that data in it. It's called US median income. 2023 was the last date I could find, but that's still relevant. You just look for the lowest one with the Trader Joe's. So here's this kind of data. All right, what is in this table? Let me turn up my brightness. Why is that not working? Oh, there it goes. So what's in this table is median income. So like taking everybody's income, you find the median of that 50th percentile, and the first few rows in the table are states, like the median income for a state in 2023. But then there are several thousand more rows. They also have cities in each state. Okay, the median income for cities in each state, and so if you look, income dots show like 60 of them. You'll see it start going into like here's all the states and things and all the like. Um, Puerto Rico is included, but they don't have data on it. And then you start getting into actual like cities and out in the first alphabetical state. So it's got city data as well as state data. I really just I care about cities with Trader Joe's in them. So let's get rid of the states. All right. So it looks like the first 50 states we don't want. And then you've also got DC. So 50 plus that one plus Puerto Rico. That's the first 52 things I don't really care about because those aren't cities. So let's get rid of those. Okay. So I'll say income dot, let's take everything from index, like from the 52nd thing onward, or the 53rd thing onward. So a range, so index 52 will be the 53rd thing because it starts at 0. And then go until the end, income dot num rows. Something like that. And like put that back in income. Make that my table. So now if I look at it, it starts with the first city. Did I do it right? Yeah. CDP stands for Census Designated Place. Not quite a city, but it's interesting. They do like this is how the census works. I guess they have like cities and towns, like they mark them in the names themselves. Interestingly enough. And let's go figure out Fresno, right? Because Fresno's in this data set for sure. So let's go find it. It's going to be called like Fresno City with a lowercase c, comma, California probably. But we can find all the Fresnos. There's multiple Fresnos in the US. So go to the income table where the geographic area name, or column 0 for short, values are containing, right? And where Fresno's somewhere within that. So there's that. Looks like there's 1, 2, 3, 4, 5, 6 of them. One has no data. Centerville is apparently part of Fresno County. I don't know where that is. But there's Fresno, little city, California. And in 2023, this was the median income for somebody living there. There's a bunch of different other Fresnos. Some of them aren't cities. They're census-designated places, but I guess the Fresno in Texas makes a little bit more money. There's also a Los Fresnos in Texas. There's a couple of them, weirdly enough. So that's a thing. So that's Fresno's data. There's also Clovis, right? We live, the name of this college, though it's not located in Clovis, has the word in it. There are two Clovises. We got our Clovis, and then you got New Mexico's Clovis. They're both cities, but I guess ours is a little bit more affluent. Now we know. But yeah, that's that. There's also some of these dashes, right? Some of these data points have no data. Like Centerville had Fresno in it. The dash meant it had no estimate for income. So that's a bit of a problem. All right. So if we have no data, like I can't do math on this. I can't find the maximum of a bunch of rows with some dashes in them because dashes aren't numbers. So I want to do number stuff, right? I want to find the minimum. I'm going to try to find the cities with Trader Joe's in them and get their median incomes. And like if there's dashes involved, like I don't want that. So let me try to fix up this income table where if there's ever a dash for the median income estimate, let's like replace it with a number or even just get rid of the thing. So I want to do something with these dashes because I can't do math on them yet. Okay, I hope that makes sense. I want to clean up the data. That's going to be a huge deal as a data scientist. You're going to get sometimes you don't have the answers, right? And then other ones were nans, right? Puerto Rico is a nan. I'm sure there's more of those. So dashes and nans, those aren't numbers yet. So let's fix all that. So here is something you don't have to fully understand, but I'm going to make a function that might make a little bit of sense, hopefully. I have lost the ability to click on this program. I might have to restart it if I go back. There we go. Okay, something weird happened. So what I will do is I'm gonna make a function that I'm gonna apply to this row that turns like this into like a -1 or some number, so I can do number stuff. So I'll call it fix. Fix this column. Fix this number. Given this thing called x, try to make a number out of it. If it's not already a number, turn it into -1 or something. So here, like I really want to like turn the thing into an integer. If you remember how to do that, like that's a thing. Call the int function on it. It'll turn that thing into an integer. I'd like to do that. You don't have to understand this function, but this is what is necessary. You have to learn what is necessary to make it work. So don't worry about it. I'll try to explain this. Like try to turn this thing into a number, but it might just be a dash. So if something weird happens, except when you can't, call it -1. That's kind of how I want you to read it. So don't worry about understanding that function, but that's what it's trying to do is turn everything into a number, because right now they're all strings because some of these things are dashes. So it doesn't know that this column could be numbers. I'm turning them all into numbers now. So income, I would like to add a new column, or like I'd like to update this column. So to update a column, you just say with column again, but you overwrite the one with the same name. So with the column that, again, what I'd like you to do is replace it with income.apply my fix function to that old column. So it's column 0, 1 of the old table before all this happens. That's what I want you to do to the income table and replace it back into income. So that is a little weird, but here's what it just did. It turned that first one into -1. So like this entire column now is numbers, and now I can do minimums and maximums and averages and wonderful things like that. Okay. So that's going to fix that problem. So now there's always numbers, and if there's -1s, that means we didn't have the data. So it's just like, let's extract everybody from 0 on up. Let's look at the table now. So income dot where. Let's look at all the values that aren't -1, where we actually have data, where the median income estimate or column 1 values are like between or equal to, I don't know. Let's just look at all of them. Let's just do it without that thing first. So let's do a histogram on the median income estimate with like, I don't know, 25 bins, and the unit is dollar. That's that much dollars. Cool. And so you see a lot of -1s right there, first of all. Ton of -1s. And then also, it looks like some cities, they make a lot of money because this graph stretches out as far as it needs to. So like some places in the US, like they're very affluent. We could go look at them. We could totally go look at them. Go income that, I don't know. Let's sort on column 1, descending equals true, right? Show me the first few of those. You have some very, very wealthy cities, apparently, or census-designated places. California Hot Springs, probably around Palm Springs or something, right? Where the rich people live. And then you got a bunch of other places that are just like very, very affluent. And on a teacher's salary in retirement, I could never hope to live here. So this is fine. I'm just going to exclude all of those. All right. And then also we have the -1s. So like the -1s are ruining this right now. It's like there's a huge spike here. So let's try to fix that too. So what I can do is I can extract those. I guess I could drop them. So income.where, all those median income estimate values, so column 1 values, are, let's say, between or equal to, we'll do 0 to like $100,000 in 2023 money. That seems more normal, and I forgot a parenthesis. So I'm just exploring the data, right? I'm just exploring the data, and this looks like a normal histogram now. So up to 100,000, you've got, and you see like in the country, it looks like in 2023 was about, the median income was about $30,000. You see the spike there. And yeah, all these things, you have access to these documentation pages, right? So if you forgot how to sort stuff, how to make a table, you will have access to all this as you're taking the test. So I did the descending equals false. We did a histogram stuff. .hist. I said I want that many bins. The unit was dollars, so it puts that in parentheses right there. Are there any questions about how I made all these things? Like these graphs, these sorted tables? Is this familiar to us still? Review? So yeah, now I've got some data, and I want to tie it to Trader Joe's locations. That is my goal right now. So I've made a table of every Trader Joe's location from last year. They might have made more, but that's okay. This is decent. I'll make a table called TJ's. So I scoured their website for every single location. And here's what I made. I made this table. So just, there's a city column here as every city where there was a Trader Joe's last year. All right, because that's when I made this data set. So I want to match over, right, all these cities with all these, with their median income estimates, right? And so if I go looking for Birmingham, Alabama, in this table, do you see how it's going to not look exactly like Birmingham, comma, space, AL? In this original table, it's gonna look like Birmingham, lowercase city, comma, Alabama, all spelled out. See how those don't match? So I want to join the tables together on those values. Remember that idea? I want to do that kind of join, and so I'm going to have to turn one, like this one, into this looking way of writing city names and states, or this looking way into writing this way of making city names and states, and like adding a lowercase city next to it. It's weird. So let's do something like that. Let's expand, right? Let's turn one thing into another thing. So let's turn these guys into like Birmingham, space, city, comma, Alabama, all spelled out. Something like that. So what I have for all these city names, like if I had Fresno, is Fresno, comma, space, CA, yeah. I want to turn that into Fresno, like lowercase city, comma, California, all spelled out. Like I want to split this into the city name and the state name. I'd like to do all that kind of stuff. And so let me just show you again. You don't have to remember this. This is just Python stuff. I want to just show you what we need to solve this problem. Okay. So there's a way to split strings, if you remember that. I think we talked about it once upon a time. I want to split it on the comma. And what it will do is it will turn this string into a sequence, like an array, it's a list in Python, of the two things. We split it on the comma, so it's like it finds the comma, and it gives me everything between the comma on the left and on the right. So I get the Fresno as one of the pieces, as the first index, and then everything after the comma, which was the space CA. So I still get that space as the second thing. So that's the split operation on a string. And I can get pieces of that. There's like a dot item in this kind of list thing. It's these square brackets. So if I want the Fresno, that's square brackets. I want the 0 things, like a dot item 0. And if I want the California, which has a space in it right now, unfortunately, but we'll deal with that. The space CA, I can get that. That's index 1. Okay, so I can split those things. Again, I'm not going to test you on the split operation, but this is what we need, because I want to make these correspond, right? I want to find Gilbert, Arizona in this table, and it doesn't look like that, right? I need to get them to look the same. So to get rid of this space in the CA, there's an operation on strings. So this whole thing results in that string space CA. If you say dot strip, it strips the spaces around each side of a string, and so that brings me back to just normal California. So that's perfect. Okay. And so if I want the city part of this table, I'll split and get the 0 thing. If I want the state part of this, these cities, I gotta split on the index 1 thing and then do the strip process. So I can make functions to do that. So you give me a string, I'll give you the city part of that string. So I'll call it def get city. You give me some string s that looks like that, like Fresno, comma space c. I'll give you the city out by doing this process to it. I'll return that. Where the city is, where the whole thing is, it was called s. S dot split on comma, give me the 0 thing. And I can do the same thing to get the state back. So get state as an abbreviation, right? You give me a string that is that city comma state abbreviation, then I'll do this too. I'll return back to you that city comma state split, get the first index 1 thing, that's the state abbreviation, strip the white space around it, so I have it just it by itself. And so this is how I can get the pieces that I care about. Right, so if I say get city on Clovis, California, it'll give me Clovis. If I say get state abbreviation on that kind of string, because there is also Trader Joe's in Clovis, it gives me that piece. And so that's me getting closer, right, to extracting the pieces that I need from this data to make it look like this data so I can correspond and find the median income estimates. Yeah. Does my goal make sense still? It's like these names or these cities do not look like these names or these cities. I have to get them to be the same so that they can join together. Okay, so the next piece is, all right, I got CA, but in this table, it's spelled out as just full California. So I made another table that will give me the state abbreviation. So here's that table. State abbreviations.csv. So I'll call that state. Oops. Abbreves. And it looks like this. Okay, Alabama, name, abbreviation, AL. So now I can cross-reference, right? So if I want to, like I had the CA, I got the state abbreviation, it was CA. How do I get the California? I can use this table from it, right? I can say, all right, go to the state abbreves table, go find where the abbreviation. It's a little ironic that the word abbreviation is a very long word. It represents something that's it's supposed to be short. Where the abbreviation is California, where is CA, that will give me this whole thing, right? And I just want this piece. So go to the name column, get the first thing, right? That'll give me the full California. Dot row 0, right? Give me the name part, item 0. So I do that on just CA. I can use this table to get the full name of the state, and I could turn that into a function, right? You can totally do that. So I can make a function for that. Def get state. So you give me a string that's that city comma state stuff again, like Fresno comma space CA. Then again, I can give you that state abbreviation. Whatever that, I can get the CA out by using my get state abbrev function that I made on that string, and then do this to that abbreviation, right? Where the abbreviation was whatever that was, and return that. So now, just like I had for these, so this all worked for all those. If I want the state part now, for Clovis, California, it'll pick out the CA with the get state abbrev function that we made, and then it will give me back California, the full-blown name California, which is what I like, all right? Do these functions that I made make sense? There's some more practice making functions as well. Like you give me this string, here's what I'll do to it to get the pieces that I care about out of it. And then this one's using one of our other functions that we made. So this is turning a state abbreviation in a city comma state pair to, all right, the full-blown, that's the name of the state all spelled out, because that's what the other table wanted, right? So what I think I'll do is, here's my Trader Joe's table. I'm going to split this table. I'm going to split it into the city name and the state name, because now I can do that. I have those options, yeah? So let's make a table with some columns now. I would like to make a city table with just the cities of the Trader Joe names, right? So let's take the original table, apply my give me that city function to the city column, or column 0, yeah? You could also just spell it out. It was called city. And then I also want the state separately, all spelled out. And the way I can get that is by applying my function get state to this column, yeah? See where I'm going with that? So that's beautiful. Get state. And I can apply that to the original city column or column 0, however you want to think about it, right? And so look what that does. It makes this table. Instead of Birmingham, comma space AL, I get Birmingham as a column, Alabama as the other column in that row. And so I've split them up. So this is looking more like the original table with the median income data. Yeah. Took a few functions to get there. So let's call this the Trader Joe's table then. Oops. That's getting closer, all right? And so I have this, and now I have my income table still. And they're looking closer, right? I've got city and state separately now. This geographic area name is closer to this, right? This is still all one big column, though. These are now separated. And so my goal is, like, okay, we've got Phoenix, Arizona. There's a Trader Joe's in Phoenix, Arizona. Let's go and find, what I want to do for every Trader Joe's is find the median income of that city so I can find the cheapest city to live in with Trader Joe's. Okay? That's what I want. So let's make that happen. I would like, how do we use this table now to look up Phoenix, Arizona, right? So you know what's going to be called? It's going to be like Phoenix space lowercase city comma Arizona all spelled out. That's what it's going to look like in that table. So like if you gave me Phoenix by itself, you gave me Arizona by itself, because that's what I have now. I have a column with just Phoenix, I have a column with just Arizona. What if I just do 2 lookups, right? Watch what I could do. So income, here's the income table. Go find all the Phoenixes, because like just like Clovis's, I'm sure there's, in Fresno's, there's probably multiple Phoenixes. Let's go find those. So where geographic area name, values, just have Phoenix in them somewhere, are containing, right? Containing Phoenix. So here's all the Phoenixes. And do you see if I, on this table now, search for all the things in this row that contained Arizonas, I'd find the first thing being the one I cared about. So take that result so far and do it again. So where the 0th column values also contain Arizona, do you see how that's going to whittle it down to the thing I wanted? And the median income is like, go to the 0th row, go to the item 1 of it. There's the median income for that city, yeah? That's going to be the answer. So now I have a process. You give me a city name, you give me a state name all spelled out. I can find for you, I have a way of getting for you the median income for that city, comma state. Yeah. So I can make a function for that. So get median income. I think you can see the process, right? City for a city and a state. Give me a city name and a state name. Then get all these results, right? Because there might be multiple, who knows? Results equals, go there. Income where 0 are containing the city name. And then also containing the state name, and usually that will whittle it down. But sometimes there's still many options, and sometimes there are no options because sometimes it's like I don't know the best way to show this to you, but there are gosh, I'll show it to you in a second. I think sometimes there are no answers, and I want to show that to you. But let's do this. Let's do it full out first. So like, all right, if we have something in results, then I want to do like, all right, return this results table is going to be row 0, right? Go to row 0, or I guess column 1, the first thing, right? So column index 1, there's the median income values. Go to the first thing because that should be right in theory. Item 0 of that. That's my answer. But sometimes this won't work because sometimes there is no result. What's the best way for me to show that to you? tjs.show, let's do like 25. There are some values, especially in California, at least I can show it to you. What's a good one? Like Brentwood. Where is Brentwood? Do we know where that is? I think it's in LA. I think it's a suburb of LA. Like that's what I'm trying to tell you right now. Like Brentwood is not going to be in the table for median income because it's separated by actual city, comma states. For Trader Joe's locations, they're going to spell out the neighborhood of LA because they have so many Trader Joe's in LA. We're not going to find Brentwood is the idea. So sometimes this table result will have no rows. Okay? That's what I'm trying to say. So if that happens, let's just mark that for us to come back and deal with manually. So if results.numRows values, like if it's greater than 0, I have an answer. All right. Hopefully it was just 1, but we never know. Go to the first thing. Otherwise, return 1. Does that make enough sense? That's what I want. You give me a city and state, I'll give you the median income for that city and state by looking up it in the table. Okay. So in theory, that will work for most things, right? You go to the Trader Joe's table with a column called median income now. Median income. We go to Trader Joe's.apply, right? What I want to do is apply this function to the Trader Joe's table. I have the city in column 0, the state in column 1. I also call them city and state. And those are the 2 things I need to give to this function. Give the city column, then the state column is the 2 arguments to the thing. And it's going to go off and it's going to work, so it'll take a while. So I should call this something, TJ's with income. It does take a second to look through, like, for each one of the Trader Joe's locations, it's got to go through 30,000 results in the other table. That will take a second. But sometimes it won't be perfect. But it's going to work for a lot of these. Right? It'll find Birmingham, Alabama. It'll find Hoover, Alabama, Huntsville, Alabama. All these places. It finds Phoenix. Unfortunately, it won't find Fresno because if I show you a few of them. I'm just exploring the data, trying to do what I want, right? Because I'm getting close. With income, let's do a sort by, because I want the lowest median income, right? I want to live somewhere. Here's all the places with Trader Joe's. I want the lowest median income for those places. That's where I'll move to. If I sort by it, I got a lot of -1s And this is exactly what I was trying to say. Like North Hollywood, suburb of Los Angeles. La Jolla, suburb of San Diego, right? All these things. I could have sworn that La Cañada was a city, but I guess that's not in there. And Fresno also is giving back -1 right now. Why? Fresno's giving back -1 right now because of the way I'm finding this stuff. It's doing this process, right? Oh gosh. And there's multiple Fresnos if you do this process in California, unfortunately. It's like, all right, where it contains Fresno, where the state is CA. So you might have to whittle this down. California. It looks like this Centerville thing, which has the word Fresno County in it. So it has both Fresno and California in it. It comes before this one, and this for sure was nowhere in the table. So that's unfortunate. It was in the table, it had a dash, right? We replaced that. So I guess if I got rid of the -1s, maybe this would have worked for Fresno, but for the others, for similar reasons, it wouldn't have worked. Okay? But yeah. That's a start, at least. You can go clean up all the -1s now if you wanted to. But we made a bunch of functions that kind of got us close to where we want to be. Does it make sense how we got to here with the cities and states and their median incomes? Like, we're looking it up, we're cross-referencing it. In the other table, we had to do a bunch of string stuff to get to here. So yeah, this is fun for me, at least. Show me the lowest median incomes where what's above -1, okay? So let's go to TJs with income. Let's sort in a different way. Still sort, but first get all the values above 0, right? Where the median income column values are above 0. And so it looks like, and let's show a few of them, show like 25 of them. Because what I want to show to you, things are happening. It looks like what I should do if I want to retire is move to Fairfield, Connecticut. Because everybody only makes $4,000 a year there. Must be some sort of utopia where you can get by. There is a few issues, like you still have to explore this data, because this is not the right answer, right? I'm not going to move to Connecticut. If you look up these first few rows, some of these have the word in the name that's important here. Most of these first few rows of cities are entirely populated by college students who have no income, usually, right? And so it's bringing down the median. So like Fairfield, Connecticut, there's probably a college there. State College, Pennsylvania, you better believe there's a college in that city. College Park, Maryland, there's a college there. East Lansing, Michigan, honestly might be a city without a college. I'm not sure that. Maybe that's where I want to move to. But like you're getting there, right? Kalamazoo, Michigan, I'm pretty sure also has a college in it. Gainesville, Florida, Corvallis, Oregon, yeah. These are all like that. That's where Oregon State is. All those things. So you got to whittle those out too, probably. Athens, Georgia is another college town. SLO technically is also a college town. You know that you can't live on that usually. So you do have to whittle this down some further, but like this is a good start. This is a really good start, and that's funny. So the first two, at least, for sure, they're cities containing mostly college students. So the first two are cities, but they're populated entirely by college students. Like if you go to UC Santa Barbara, like I did, there's a town right outside the college called Isla Vista. You've heard of that? Populated entirely by college students. So I'm sure that the median income is also quite low, because people are getting money from their parents a lot of the time, right? That's a thing if they're not working. And so that kind of brings down this number artificially when really you couldn't live on $4,000 in Fairfield, Connecticut. No way. But yeah, maybe East Lansing, Michigan is where I must land, all right, when I retire. Plenty of water, at least. And so that was a fun process, right? We had some data, we had a thought. We gathered the data, we cleaned up the data based on those thoughts. We had to figure out how to get this data to correspond with my data for Trader Joe's locations. We saw the makeup of the U.S. Economy, and based on the city in 2023, looked at all the Trader Joe's locations, and we tried to match them up by doing some string operations. We made functions upon functions until we could apply one last function to get what we really wanted, right? And even then, it wasn't perfect because, like, Fresno was still -1 because of those issues, right? But we ended up here, and that's a good start. We can clean up the rest manually, and that is just the fact of life as a data scientist. Sometimes you gotta look at the thing and figure out, all right, where to go from here, how to get the last mile towards where I want to be in my final answer for my boss or something. So yeah, I think that's a fun little review of just like table stuff, function stuff. Are there any questions about that before I move on to like more stuff? I want to go to hypothesis testing next if we're ready. So I want to review like those fancy functions, like they're all in this table, right? So where will we find like sample proportions? I don't know if I'll go over minimize today, but that kind of stuff, right? We talked about that. And probably we'll get into sampling from a table. Where is that? Because it's all on this table. Yeah, it's all here somewhere. Table.sample. So that's all there. Yeah, let's go over the Mendel experiment. I think that would be a good one to start with. So this will, again, it's a review, but let's remind ourselves of the idea, because we have a question. We want to figure out what is the likelihood of this having happened. So we have a hypothesis, an alternative hypothesis. We want to calculate a p-value. How unlikely was this based on our null hypothesis? So let's remember all these words, right? So, okay, Gregor Mendel, he grew exactly 929 pea plants, and he found that 705 of them that he grew had purple flowers. The rest were white. Those are your two options. And so if you do the math, that's almost a little over 75%. And he's like, I don't think that nature is doing things on 7,589 over 10,000. Nature's probably doing things on 3 over 4. So his model, in his mind, right, was, all right, there's probably a good 75% chance that a flower, any given flower, will be purple for a pea plant, and a 25% chance that it will be a white flower for the pea plant, regardless of any other colors and plants. It's just like, that's how it was going to be, all right? So that can turn into our thought, right? Our null hypothesis is something that we can end up simulating, at least in this class. It's something that we can simulate. It's based on random chance. There was nothing other than random chance that gave us this answer, right? Null means nothing. There's nothing other than a random chance. So our null hypothesis is that Mendel's model of the world is perfectly correct. That extra 0.89% was just due to complete random chance. Just like when you flip 100 coins, you're not going to get exactly 50 heads. You probably get like 51, 49, right? So it'll be very close, though, which is kind of what he saw here. So that's our idea. The alternative hypothesis is the opposite, right? It's just like, all right, if his model is wrong, there is an issue. There was this 7589 was meant to be there. It wasn't just due to random chance, right? So how do we measure the difference between what we thought it should be and what we found? We have to come up with a statistic, right? So our statistic will be, let's just like do a difference. How far away was what we saw from 75%? Because that's what Mendel was thinking. So let's zoom in on the idea of purple flowers. You could also zoom in on the idea of white flowers, because it's either one or the other. So let's figure out, let's see, like, all right, let's get proportions of purple flowers, because we're going to simulate, right, some randomly generated gardens, assuming that the null hypothesis was true. There really was a 75-25 split. See how many purple flowers there were, because it's never going to be a perfect 75-25 split when you do the simulation. Just like if you flip 100 coins, most of the time you are not going to get exactly 50 heads. So let's see what our generated things are, and then we'll go from there, all right? So, yeah, I think what we want to do is we want to see how far off, right? How far off this stuff was. So let's see. What's a good example? So like our differences, so our statistic that we're going to be calculating is how far off were we from 75%? All right, so like let's go simulate a garden, right? Let's go simulate a garden of pea plants, and we'll find that that garden simulated under the null hypothesis of a 75-25 split had like exactly 76.8% purple flowers. the way that we'll calculate our statistic to see how far off we were from 75% was we'll just subtract 75 from that. And then also take the absolute value, so that if this were a smaller number, right, if it wasn't like 76.8, if it was like 73.2% for this simulated garden, we'd still get a positive number, right? How far away was it from 75%? Okay? And so let's get started with that. Do those words ring a bell? Make enough sense? You remember them? We've used them well enough? Long enough? So yeah, let's simulate some pea plants, some gardens. So Mendel's model was there was a 75-25 split. So we're going to make an array because that's how we call sample proportion, 75-25. So that was our proportion of purple flowers, comma, our proportion of white flowers. Let's call that Mendel proportions. Is that? And then the proportions of purple is what we're going to do our simulation with and compare against. So the purple bits is item 0 of this. So Mendel, this is being a little wordy, but that's okay. Mendel proportions purple is go to here and get item 0, because that's going to be how we do this game when we simulate. All right. So what we will do now, so we need those things in order to get what we want. In order to generate a garden, we say sample proportions, right? Let's go to the documentation, because just in case you forget, you can always go to the documentation. Sample proportions takes a sample size and then your model proportions. So those proportions better add up to 1. So we're going to grow exactly 929 pea plants. We want to repeat the experiment, right? Assuming that Mendel's model was correct. So use his proportions. If I hit enter, this is what I find. I find 76.9, almost exactly my first guess. That is how many purple flowers there were in this generated garden. This is how many white flowers there were. Those were the proportions. Okay, does that make sense? That's what sample proportions gives to us. If I rerun this, of course, I'll get a new garden. This time I got fewer purple flowers than 75%, a little bit more white flowers, therefore. And so I want to grow a bunch of gardens and see how, like assuming that there was a 75-25 split, see how far off I was each time. Because if under the model I usually get around this far off, then the model's good, right? It predicts this garden that happened in real life that Mendel saw. It wasn't this didn't have to be due to something other than chance. So there was firepower towards the null hypothesis. That's what we're trying to do. Okay? Does that process make sense? I just want to do a bunch of simulations and count. Like I want to keep track of like how far off was I each time. So my distance away from how far this was, right, was you take that and then you do subtract the purple amounts, right? Subtract the purple amounts. So you do that, and then so like sometimes that's negative, so you do absolute value. Give an absolute value there, and like that's the number we care about. Keep track of all those distances, and so let's simulate a bunch of these kinds of distances. So say your book likes to prefix the functions that do this with 1 underscore. So like, give me 1 simulated distance for a simulated garden. Takes nothing. So okay, let's call sample proportions here. Get the purple amounts, right? So item 0 of that. And that's like sample proportions purple. How much purple was in this generated garden. And then what I want to do is I want to take that amount and give me the distance back from that proportion of purple in this generated garden, subtracted by the 75 that we thought it should be, and see how far apart we were. Right? That's the distance away from our thoughts of what it should have been. And so it's like, all right, it's 0.004 away. This one was 0.142 away. The original one, what was our observed distance? We can do that, right? Our observed distance that Mendel saw in real life. It was, all right, 705 over 929, so like this value, 0.7589. We can have Python do the math. Subtract that from 0.75. Take absolute value if you need to, but this one's going to be bigger, so we don't need to do that. So the original observed distance was 0.00888, so that's interesting. We were able to simulate a garden that was even farther away from this that we saw in real life. So That's looking good for our model, right? That's looking real good. So let's simulate 1,000 gardens. 1,000, 5,000, 10,000, these are all good amounts. Do it a few times. So I'll say repetitions. So I'm going to loop now. And I'm going to keep track in an array of all these simulated distances. And that's what we did to do this kind of hypothesis test, where I in NP a range, that many repetitions. What do I want? I want to call one simulated distance and append that, right? NP append to the distances array, that new distance, and set that back into distances because np.append does not update anything, all right? So now I've got 1,000 things in this distances array. And if I put that into a table, I can do a histogram, right? Table with a column. And what if I calculate this? The distance between my sample percentage, sample proportion of purple, and 75%, right? The thing that I thought it was supposed to be. Those are my distances. I get this big long table. Oh, sorry. I got to spell with column properly. I get all these distances. There's 1,000 in them. And then if I do a histogram, you can see how far apart we were, usually. So it looks like we get, in some of our simulations, in our simulated gardens, we get far, far away, like 71% purple. Or, in the other direction, 79% purple. I don't know which one it was because I did absolute value, right? But somebody's over there, maybe on each side. So that's interesting. That's cool to think about. Of course, it's close to zero because usually, like you flip 100 coins a bunch of times. Usually, you're going to get very, very close, right? Distance 0 to 50 heads. That's going to be the most proportionate thing, but you're also going to have things on either side. So that's what we've done. And what was our original distance? It was, our observed distance was 0.008, so like a little less than 0.1. That seems pretty likely. That seems pretty darn likely. So to calculate a p-value, our p-value, remember what it does is it's going to like try to figure out what was the likelihood of the null hypothesis like generating the value that we saw in real life that we thought was weird, or something even weirder, right? Something even farther that would point us towards the alternative hypothesis. So to spell that out, the p-value in this situation is like trying to figure out a proportion, like how often did pure randomness give me what we saw or something even more extreme, right? How often did randomness from our simulation, because that's what your null hypothesis is all about, randomness, generate the observed distance that we saw, which is like 0.888. It's a fun number. Observed distance. Or something even more extreme. That's always, you got to think about the direction, right? Something even more extreme. So what was the direction of it more extremeness in our situation? It would be something even bigger than this, right? Because we thought that 75 was the answer. So this is like bigger than 75. That was a big distance away. So something that distance away or even farther. So it's going to be towards larger values. So start at your observed distance is 0.0088 and look like how often did I see something that or even bigger, right? Because that would be even farther away from what I thought that the null hypothesis was going to do, right? From the 75-25 split that we thought it was. This direction would be even like a weirder split, not 75-25. Does that make sense? That's the right direction. It wouldn't be to the left, it's to the right. And that's how we'll calculate our p-value. It's like how often, because we got all these distances, right? How often did our distances, were they exactly equal to, right, to our observed distance? Or even bigger, right? Because that would be even more wonky farther away from the 75-25 split, because it's the distance from 75-25, right? How often was it that? So I get a bunch of trues and falses, and if I count non-zero that would be a number of those, right? How many trues and falses. And then for a proportion, I have to divide by how many times I repeated this. So like by the size of distances or just by the number of repetitions, because that's the same. And it looks like over 50% of the time, did I get a value that extreme or more? And my model of just assuming a basic 75-25 split and letting randomness take the rest gives me it that often, which is great, right? What do we conclude now? Usually, with a p-value of 0.05, like 5% chance or smaller, that's when it becomes statistically significant. That's when the model probably isn't a good model. It's not predicting the observed thing that well, only like a 20th of the time. This is doing it over half of the time, right? Our model is predicting what we found in real life, what Mendel found, something far away, somewhat far away from the 75-25 split, under the assumption that it really was exactly 75-25 and letting randomness take the rest. Yeah. So our conclusion then is we are going to hold on to our null hypothesis. We are not going to reject it. As the wording is weird. I know you've read it a bunch of times now, but our conclusion now is we do not reject the null hypothesis. All right, or just the null for short. The reason we don't say, right, that it was the null hypothesis is exactly true is because, like, we don't know the real value. Like, we don't know how. I guess if you're a geneticist or whatever the word is, maybe you do know that this is perfect. But maybe it was like a 74.9 and a 25.1. We just happened to, our model still predicted it, right? Like, this doesn't have to be the ground truth. Our null hypothesis doesn't have to be perfect. We just don't reject it, all right? We don't have any reason to believe that the alternative was the right answer. That's what we say, okay? Not to say that the null was exactly right, but there's no reason to discredit it. It's kind of like you're being very cautious in this kind of statistical test. But we've answered the question that we had. Like, could it have been a 75-25 split? Absolutely. Was it? If you learn about genetics and biology, yes. But we didn't have to know that. Okay? So that was our hypothesis test. Does the process make sense, what we have done? How we did it? It's also very important to simulate just as many pea plants as Mendel did, because you don't want to throw off the numbers in any weird way. Because you know that, if you grew 50,000 pea plants with this exact split, you get really darn close to 75-25, right? Assuming that was the percentage. If you grow 100,000 pea plants, you're going to get almost a perfect split, because all of the weirdness is going to have been averaged away. But 929, that's not too bad, right? I hope that makes sense. Any questions about that? So that's the first example of hypothesis testing. I think I have enough voice left to do one more, and that's good timing anyway. Ready for that one? I just want to do a different kind of hypothesis test. Let's do a permutation test rather than using sample proportions. Okay? Let's do serial, near and dear to my heart. So here, we've got our serial table. And we noticed long ago, it's been so long now, but it's a good example, that, all right, here's my serial table. We looked at the rows, and we found that the aisles had some weird data in them, right? We found that the cereals on shelf 2, or something going on with shelf 2. That was the middle shelf. Shelf 1 was closest to the floor. Shelf 3 was the highest up. Shelf 2 was right in the middle, apparently at a toddler's height is what we're imagining. And we found that the numbers were a little off. So cereal, let's select out the shelf and the sugars. So that's all we need to do this. Like, shelf, what shelf was it on? What are the sugars amount in grams, I guess, for that cereal? And let's group by the shelf. And by default, grouping just counts. So there's a decent amount. It looks like there's more space on shelf 3, but that's shelf 1 and 2 for sure, very similar in numbers of cereals. And if you say, don't just group by shelf, also collect with I think it was called collect. Yeah, collect, or if you just give something. I want you to do np.average on the groupings, please. Don't just give me the count. So you see that shelf 1 was very healthy, low amounts of average sugar. Shelf 3 was kind of middle of the road, and then shelf 2 was ridiculously sugar. Yeah, we found that. We explored that data. And so enter another hypothesis test. So let's, our question is, was something nefarious going on, right? Was shelf 2 selected to be that sugary, or were they just like randomly taking things off of the back of the truck and they just happened to make shelf 2 that sugar, all right? So the null hypothesis has to do with the randomness, right? It's something that we can simulate. We can simulate some random shelf 2s, right? So our null hypothesis becomes, you know, the cereals on shelf 2, let's give them the benefit of the doubt. They were just as sugary as the other shelves. The differences that we saw, they just randomly shoved cereals onto shelves. They just happened to randomly put a bunch of sugary cereals on the shelf. There was nothing nefarious going on. All the differences to the other shelves was due to complete random chance. Okay, that's our hypothesis. That's something we could very easily simulate, right, by picking some random shelves, or picking exactly what, I guess I got rid of, I think there were 21 of them. 21 random cereals, right? Making another random shelf 2. So that's our null hypothesis. And then our alternative hypothesis is something in the other direction. We're saying that no, the shelf 2 cereals were selected to be more sugary. And so as we're going to do our simulation, we're going to calculate a statistic, we don't want to do absolute value anymore. We don't want to say that shelf 2 cereals were selected to be far away, like the sugar amounts on shelf 2 was very different than shelf 1 and 2. We're saying no, they were different in the direction of they were more sugary. They didn't have to be less, they were more, all right? So I don't want a distance anymore. I want to know how far away were they, right? In the positive direction. How more sugary were they, all right? So that's going to change the way this statistic works. We'll get to that in a second. But a good way to make this happen is to do a permutation test, because I have all these labels, right, for shelves. I know what shelf all these cereals are. I can generate another random shelf 2 by just shuffling those labels for shelf, right? And I would assign shelf 2 to some other cereals that weren't potentially already on the thing. So that's how we do that. So how do we make this happen? We take our cereal table, we get the shelf column, and we shuffle it, right? So we say, we take a sample, right? Sample the table without replacement. So we have just as many things on shelf 2 as there were before, right? I'm just shuffling the cereals, the order of them right now. I'm not duplicating anything. So I'm keeping the same amounts on each shelf. And then if I get the column, called shelf, now I've got a bunch of different orderings for what shelf the original cereals could be on. See that? It's different every time. I don't know why the first one's like to be on shelf. There's a lot of things on shelf right there. This is what I want to do to every cereal. Right? This is take the cereal table, add a new column, and we like to call it shuffled label. Right? And we made it this. There's our new shelf for these cereals. So like, all right, the original shelf for this cereal is 3. You're going to be on 1 now. The original shelf for this next cereal is also 3. You're now part of shelf 2. So I'm making a new random shelf 2 with just as many things by shuffling those labels. This is called a permutation test. And then if I go to the new shelf 2, right? Oops. Where shuffle label, the value is 2, like the shuffled, like the new shelf 2. So here's all the cereals on my new shelf 2. Some of them came from other places. Some of them are also originally on shelf 2. This one was on shelf 1. Now we've randomly placed it there. This was on shelf 3. Now we've randomly placed it there. Then go and get the sugar amounts for these cereals, right? Call them sugars, not mean. Here's the average amount of sugar for this random shelf 2, right? And it was not close at all to the 9.6 grams of sugar for the original shelf 2, and this was a simulated shelf 2. Does that make sense? If I do it again, this time I do get a decent amount of sugar. So it goes to show, like, it depends. It looks like it's a little under 7 most times. Any questions about how I got this? You see how we're doing the permutation? I've permuted the shelf label, so I've assigned a new shelf to the existing cereals. I've got just as many, right? Just as many. And now I want to do this a bunch of times, right? I want to do this process a bunch of times, so let's make a function that does it. That does exactly this, just like a few thousand times. So def, give me one simulated average sugar amount, one simulated average. And I just want you to return all this. So it's a little ugly, but just do that code all over again. And then I want to do exactly what I did before. I want to keep track of, like, let's do 1,000, not not these, but different values. We'll get to that in a second. So here's this. Let's see, 1,000 of them. They're not called distances anymore. They're simulated averages. Boop. 1,000 still fine. And I want one simulated average. Did I change it in every spot? I think so. So I run this. I've now got a bunch of simulated average sugar amounts for some random shelf 2s. And my goal is to see, like, how often did I get an amount of sugar on that random shelf 2 that was as sugary as the original shelf 2 or more sugary. So let's do a histogram real quick with a column. Averages, sample averages, sorry, simulated averages, my bad. And so that just puts them all into a table. And then if I do a histogram of that on column 0, let's do 20 bins a piece, we see this. So they're centered around, looks about 7 is the usual amount. That makes sense. That's kind of what we saw when we pressed Shift-Enter a few times. And then the original, our observed, right? Our observed sugar's average for the original shelf 2 was 9.6 grams of sugar. That's going to be over here. Yep. So how often did we get a random shelf 2 with that much sugar or more? Because more is the direction we care about, right? Like, you count how many times we got from here onwards in that direction, right, to the right. So we just simulated sugar amounts and we found in that direction. How often was that? Not very often. Let's see how often. So how often was our simulated average values for these random shelf 2s exactly equal to what we found on the original shelf 2, 9.61905? Or even worse, even more sugary, because that would be in the direction that would favor our alternative hypothesis, right? That, all right, something was afoot. How often did we randomly get that? Or something more extreme? How often does our model, our idea of the world, our null hypothesis, predict this to happen? Because if it does it decently often, like it did last time, like 50% of the time, then it's a good model. Maybe that was fine. It was just random chance. Well, let's see this. How often did we get this? NP dot count non-zero. How many times did we see this happen? Divide by how many repetitions did we do? Or just like the length of simulated averages. Either way works. And it looks like this happened 0.1% of the time. Not 1% of the time, 0.1% of the time. All right? Did our model predict this random shelf 2 having this much sugar or worse than we saw in real life compared to what we saw in real life? And so this p-value is disgustingly small, right? This is extremely statistically significant, right? This is very statistically significant and definitely smaller than 5%. So it's so unlikely for our model of, okay, it was just a random shelf 2. They were taking cereals off the box or off the back of the truck and just they shoved them onto shelf 2 and it happened to be sugary. We simulated that happening a bunch of times, right? 1,000 times, and only 1 out of those 1,000 times do we see something that bad or worse. See that? That's crazy. And so that means it's very unlikely for our model to have that happen. It's very unlikely for our null hypothesis model to predict what we actually saw, which means that the null hypothesis model is not a good view of the world. It's not probably what happened. We now reject it, right? That's what we say. That's our conclusion. We reject the null hypothesis in favor of the alternative. The alternative hypothesis is a better view of the world. We have not proven causation or anything, right? You have to do a randomized controlled experiment for that. But we've shown that the idea of it being random chance, that shelf 2 was this sugary, is out the window. It was not just random chance. There was something else happening. We don't know exactly what. We can guess, right? We have some thoughts. But we definitely reject the null hypothesis in favor of the alternative. In a universe where those were the only 2 options, the alternative is the correct option, all right? Well, we don't know what really happened. We just know that the null was very unlikely. That was probably not the way the world worked, and so we have more firepower in terms of the alternative hypothesis. We therefore reject the null in favor of the alternative. And so that's another hypothesis test. That's all right. We had a question like, all right, were shelf 2 cereals more sugary? It looks like they were. So they were selected to be a bit more sugary. It was not just random chance at the very least. That's pretty fun. Any questions about that example? Do you see how p-values are working as well? How you're calculating it? It's always, you're going, all right, and you're like, how often did we simulate a value that the observed value? How often was it equal to that or farther in the direction that would point us towards the alternative? So in this case, it was greater than, because that would be even more sugar than we really saw, right? Even worse, even more sugary. So that's just something to keep in mind for the final. And I think that's where I want to stop for the day. So we'll go into more things next time. We'll talk about confidence intervals. We got bootstrapping, we got regression, we got classification, Bayes rule, so many options. I have some fun examples, some of which we have not seen before, just to keep it exciting. But I think this is a good place to stop for now. Any last questions about what we've done so far? Because we'll pick it up next time. All right, so just want to remind you of all the things I talked about at the start. If you have any late work to do, make sure to get that in by this Friday at midnight. And yeah, the next thing for us is going to be Wednesday, more final review. And as far as assignments go, remember, we've got something due on Wednesday. That was lab 10. And we got 2 things on Friday. Project 3 is the one that's actually for a grade. Homework 12, remember that I will give you extra credit if you do that one in time. Can't turn it in late or anything, since Friday's the last day to turn anything in. But if you want to do homework 12, I'll give you 1 percentage point of extra credit. Okay? You also have the extra credit assignment to do if you'd like. But yeah, we are getting close to the end, you guys. And I think that's all that I wanted to say and record for now.